A very good morning to all of you. You've already met Dr. Prakash Arumagasamy many times, and he's one of our very valuable colleagues at the TLC. Just to give a little bit of background, he worked on rotation-powered pulsars in X-rays for his PhD at the Pennsylvania State University. He was at NCRA for a few years before joining the Teaching Learning Center at Ayuka. For those of you who are from an engineering background, Prakash also started off with an engineering degree in mechanical engineering, and and has done well in astronomy and astrophysics and teaching. He's very passionate about the way we teach and learn, and it's a great pleasure to have him with us at TLC. Today, he's going to talk to us about electromagnetic wave propagation in plasma, as you can see over here. And he's also put a little blurb over there saying that keep a notebook and a pen handy. So if you haven't done that as yet, please do so and work out small things that he's going to ask you to do or ask us to do. So Prakash, please start off. Thanks.
Thanks a lot, Saitya. Welcome everyone. Good morning to all. As introduced by Saitya, we're going to talk about electromagnetic wave propagation in plasma today. And it's going to be a sort of hands-on session. We're going to see in depth, particularly focus on one of the solutions that is, I believe, sort of the stepping stone to understanding the larger picture of plasma, not just about its propagation effect, but in general to understand plasma. I think this is a good start. So if you haven't already done so, please have some sort of paper and pen handy. It's mainly to ensure that, trying to get across derivations in a lecture. If you're just viewing it, I'll very soon lose you in a couple of slides. So there are little bits here and there where I have left out blanks for you to work out on your paper, and then I'll show you how the result comes about. So if you do this, I think you can keep track of what is going on for a slightly longer time, hopefully. So, okay, let's get into it. I'll just introduce by sharing, I'll start with a word of appreciation for plasmas. I would want you to think about what fraction of the visible matter in the universe do you think is made up of plasma? Now, if you don't already have read about plasmas, it is very likely that your number is going to be smaller than the actual number, actual percentage, if you want to do in percentages. And you can be excused for it because if you see day-to-day life on Earth, you do not encounter plasma as much. At least a few decades ago, plasma was there in a lot of everyday instruments as well, using lights and televisions and all that. But now we have shifted quite a bit to using semiconductors and solid-state devices because of the power efficiency, and we don't use even that much of plasma anymore. You can still see in a few neon lights, electric discharges, or high industrial applications like even fabricating chips and trying to create plasma fusion in the lab and so on. But you wouldn't see it as much in day-to-day life. But if you want to get an idea of how much of the matter in the universe is plasma, the visible matter, then even if you just look beyond Earth to the solar system, you can notice that 99.85% of the solar system mass resides in the sun, and the sun is almost entirely, it's entirely plasma. Depending on the source you look at, you'll see estimates of between 99.9 to 99.999 of the visible matter in the universe is in the form of plasma. So the little quibble is just about the little digits at the end of the decimal, but largely it is entirely plasma. So it is a very useful thing to study if you want to truly understand the universe. So the goals of this lecture would be to go in depth into one of the applications that is one of the simplest you can think of. and understand the effect that plasma has on electromagnetic radiation. This is by no way, although it's simple, it's the first non-trivial step you can take to understand it. And it's of special relevance to radio observations, as you would have heard about it quite a bit in the last few lectures. In the process of this, you'll also learn the techniques, some of the techniques, at least in these simple situations, how one goes about deriving the effects and finding solutions for electromagnetic wave, how electromagnetic waves propagate in plasma. But such techniques can also be extended to complex situations, as I'll slightly allude to towards the end. So we are focusing on electromagnetic waves in cold plasma, which I'll define shortly. Specifically, we'll look at the end of the lecture. We'll have derived and hopefully understood how dispersion delays come about as electromagnetic waves travel through cold plasma of the interstellar medium. So fundamentally, what you have to understand is that the radiation that is coming from a particular source consists of these electromagnetic fields, which you can focus on only the propagating electric fields. And the plasma is essentially ionized gas. And we'll define more about the conditions of the plasma that we are interested in. But it has essentially charges both negative and positive. And if we try to understand how these electric fields of the radiation affect the charges, and the charges in turn produce a resultant electric field that can propagate through the plasma, then we would have essentially obtained the solution. So to do that, it's essentially just 3 steps. If I try to go through the derivation and then look back as to what are the big steps that we took. So it is very useful to have a Fourier description of the electric field, which will come to a full Fourier description, not just in the time domain, but also in the spatial domain. And then we calculate derive the response of the charges due to this electric field. And we'll come to ideas such as the complex conductivity or permittivity, which are ways to look at some of the parameters that are required to understand the solution. And then it boils down to just solving the wave equation in that medium, in this case, a plasma, and try to see which modes are allowed and which ones are not. Essentially, which solutions are allowed and which ones are not. Okay, so to begin with, we'll take this first step, that the electric field of the radiation that is incident on the plasma, you can just do a Fourier expansion to its constituent frequencies, both in the time and spatial domains. I'll explain the spatial domain a little bit more, especially for people who are new to Fourier transforms in general, and the idea of taking Fourier in the spatial domain. And once you have that, we can concentrate on one of these components to find the omega k relations, which are allowed in a particular medium. These would be called the dispersion relations, and it'll essentially give you the solution as to which frequencies are allowed, and you can calculate things like velocities, how fast they travel, and so on. So coming back to the Fourier description, this is a picture that I showed even in one of the previous lectures, where the main thing to appreciate is that you can have some sort of time dependence of your signal, and you can always express it in the frequency space as contributions due to a continuum of frequencies or sine wave functions with a particular frequency. This is different than what one does for periodic signals, where one can use a Fourier series and you can have discrete sine curves that can combine to produce, in many cases, if not all, a discrete set of sine curves can be combined to produce the periodic signal. But in an aperiodic signal, you'll need a continuum of, usually you'll need a continuum of frequencies to do that. Now, if you understand how this works in the time frequency, so the time and the frequency are these conjugate quantities, and you can go from, you can go from one to the other and do the analysis. A description in one of the variables, for instance, time, can be expanded as solutions in a continuum of frequency space functions, sine functions, with different amplitudes and phases. Now, if you want to understand the same thing for the spatial domain, you can imagine functions to vary in space as well, not just in time, right? If you have a function that is defined in the X, Y, and Z coordinates, you can have a similar description where you are describing that particular function, let's say in the X along the X axis, and you define these sine functions which have a particular wave number, and appropriate combination of these sine waves with appropriate amplitude and phase. When they combine, they can reproduce essentially the function in the x-axis. So that is what the k-space is. This is the conjugate of the spatial dimension, where you can have these sine functions with different angular wave numbers instead of the angular frequencies that we use for time, which has the expression, which are defined according to the wavelength of those waves that are combined. And one can have a description like so for electric field that is varying in the spatial dimensions, or 3 spatial dimensions and 1 time dimension. You can expand it in terms of these Fourier components in the k space and the omega space, and the integral of it over the amplitudes appropriately determined in this space would give you back the original function. And you can see that this corresponds to a plane wave solution. You can have different forms of expansion depending on the problem of interest. But this one here uses the plane wave solution. You can see that k dot x equals constant corresponds to a plane wave by this particular diagram over here. The various symbols here does not correspond exactly to the symbols that I have used in the derivation. But you can imagine these R's are essentially the position vectors, which are the x defined here. And the S is the direction of propagation, which would be the K. The K vector, you'll see that corresponds to the direction of propagation. And the K dot X, or in this case, S dot R, corresponds to this plane. And hence, this represents a plane wave. Now, before we go into the plasma solution, I would like to just for you to just appreciate how it works in the trivial case of vacuum propagation. In vacuum also, you can take the electric field of the radiation. You can do this expansion in Fourier. The Maxwell equations that are relevant for determining the propagation of electromagnetic waves are the time-dependent ones without any charges on current, right? I'm assuming most of you are familiar with these Maxwell's equations. Now, for task 1, let's just for warm up, you guys can use these 2 equations which are coupled. You can see that E depends on B here, B depends on E here. You can take these coupled equations and try to uncouple them by creating a second. These are first order differential equations. You have to first order coupled differential equations. You have to decouple them, and in the process you'll see that you'll create a second order uncoupled equation. So essentially you'll have to take the curl of either of these equations, one, depending on which one you do, you'll get the equation either for E or B. Is that part clear? You can just do it on the piece of paper you have. I mean, this is, I understand it's almost trivial, but just in case to see whether everybody is on board to begin with, and we'll establish how we're going to go for the next processes too. So once you do that, just you can type in done in the chat box, and I'll be able to view the chat box, and then we can move on. Is that clear? So all you have to do is take the curl of the equation, let's say the one on the left, the del cross E term, and then substitute what you get for del cross B and create a second order differential equation in E, or alternate name B, which will be the same. I'll just do it myself here just to time so that I do not rush you too much. Any doubts here? Please unmute you can unmute yourself and ask, let me know if you are having, okay. I can already see somebody did it, so hopefully it's working fine. Since these are partial differentials, yeah, I hope it's clear that the time derivative and the spatial derivatives, you can switch the order. Yes, okay, I can see quite a few of you have done it. So, I mean, this one is pretty straightforward. You take the curl of either of these equations, and you, on the right-hand side, you'll get the del cross B or del cross E, which can be substituted using the other equation. And what you'll have is the wave equation. And you can see the top one here. Yeah, this shouldn't have been a problem for any of you. That's good, great. So you have this wave equation, and what one can do is assume a harmonic time dependence of the electric field, just the time dependence part, and one can try to see what solution one can you can get a solution for this wave equation. Now that would be the second task. So some of the things, I mean, to simplify the process where you may not exactly remember how to expand this vector identity del cross E. So those things are given over here, and the time dependence is shown over here. This is your second task. I'll mark it over here so that I know the dones that follow it are for this task. So I essentially want you to use the left-hand side, expand it like so, and see which term survives and which one does not. And then the second term on the left, assuming a harmonic time dependence, take the derivative and try to combine these two to see what is the electric field solution that is allowed. You can take you're considering plane waves. You can just assume the propagation direction is the x direction, x-axis, and which simplifies the del square that you have in here to the, just a simple second derivative along the x-axis. So you can work on it and try to see what you get. So you can see here in the electric field, the time dependence is only in the exponential component. This E0 defined here will have a spatial dependence alone and on frequency. So I'll slowly go over the steps. Some of them you would have already gotten, but if you were stuck at some point, it should be clear if you just look over here. The first term, as you can see, can be expanded using the vector identity I showed earlier, except right now it's in vacuum. So the del dot E term, which would depend on the charge content, will go to 0, and you'll be left with only the del square term. And if you take the time derivative of this harmonic time dependence of the electric field, you'll get the omega square by c square. And this would be the wave equation in one dimension. Were more people able to finish it? Or was there some problem? Okay, I can see a lot more dones are coming now. Okay, and this is a simple differential equation you'll solve where the solutions would be e power, plus or minus ikx, let's say. And from this, you can, it will be some constant over here times x, and you can see it has the same dimension as the angular wave number that we defined. So what you can immediately see is that the solutions that I accepted are for k equals plus or minus omega by c. And this is in a sense, you can draw this in the omega k space, and it would be the straight line of omega equals ck. And in vacuum, these are the solutions that are allowed. This is the omega k relations that can propagate, right? And the speed of propagation is the speed of light at all frequencies. Okay, so this is a trivial thing, just to appreciate what's going to come when we introduce plasma. Okay, now just keeping that in the back of your mind, where, we took the electromagnetic electric field, we had the Fourier description, and we used the Maxwell's equations to get to a wave equation, and then we solved it to find the solution. Now, as soon as we introduce the plasma, what changes is you no longer have this the simple case where the dependence of electric and magnetic fields look very symmetrical. Especially in the del cross B term, the curl of the magnetic field equation, you'll see that there is this current term, and you cannot cancel it anymore. It's not zero, because there are these free charges that can move about in the if you apply an electric field to it, right? So we will see under our assumption of the plasma how we can derive this current, and then whether we can still get something that resembles a wave equation and solve it. So,
excuse me, sir, I had a doubt. Can you go back to the previous 2 slides back?
Yes.
So here we assumed a harmonic time dependence for the electric field. So
yes.
Was this because, how did this come about?
Oh, so we just, as I explained earlier, you can have some time dependence, right? You can have some arbitrary time dependence of the electric field, which can be decomposed into these Fourier components with all constituting a lot of frequencies as a continuum of frequencies. And the technique is to just use one of these components and try to see what corresponding k wave number that you can get, which allows for propagating solutions. So it is general in that sense that you can take an electric field of arbitrary time dependence and you can expand it into these Fourier components and focus on only one of the Fourier components.
Okay, thank you.
Is that okay?
Yes, sir.
All right. So so this is the only seemingly minor difference now. In the presence of plasma, there will be a current. Now, to calculate the current, we have to understand the plasma. What exactly conditions are imposed in this plasma so that we can calculate the current. So what we are going to assume that it is cold, tenuous, ionized gas. Cold is a relative term over here because it's still ionized. Doesn't mean that it can recombine and cold in the conventional sense of neutral gas. It is still ionized, so it's relatively hot. But the importance of the cold is with respect to the kinetic energies it would have because of the temperature. Now it will have to be tenuous so that the kinetic energies are not high enough and the density is not high enough that collisions are more important than the perturbations that it's going to experience due to the electric field. So that is the idea behind imposing these conditions. that we just worry about the effect of the electric field and we do not take into account effect of any collisions, because in such a gas, the effect of collisions or the collision timescales will be much larger than the timescale of the response to electric fields. We also assume homogeneous and isotropic plasma of quite a large extent, and equal number of positive and negative charges. The study of non-neutral plasmas is a whole different field. In most cases, and especially of our interest, it's going to be equal number of positive and negative charges. A critical requirement is also the mass disparity, which may not be obvious in the derivation that follows right now, but it will become important in some conditions where such a condition may not be applicable. In our case, there is a mass disparity, which essentially means that the electron motion is only of relevance. The protons and ions are considered pretty much stationary compared to the electron motion. You can imagine cases like the electron-positron plasma that happens in relativistic conditions. In those things, such a condition cannot be applied anymore. And that, again, in turn leads to interesting results. But this particular solution will obviously not be applicable there. So what we have to concentrate now to calculate the current is just how electrons move in the electric field of the incident radiation. Okay, so that's how we compute J. There are free electrons, and the current will be defined as the number density n of electrons multiplied by E. Here is just the charge of the species. For electrons, it will be negative E, and we have to calculate a particular velocity. Right, it will be just the current will just be NeV in the linear approximation. Small perturbations, and we are looking at just the simple changes. Now, velocity can be calculated from the Lorentz force that the electric charge experiences due to the electric field, and that is what you'll do in this task here. Let's say task 3. I've shown the Lorentz force, mass times acceleration. It's just equal to the charge times the electric field. And the electric field, the Fourier, we are taking the a Fourier component of it. So you take one of the Fourier components and try to calculate what is the velocity that you will get due to that electric field component, right? That would be task 3. So essentially, it will involve one integration. You have this differential to the left, you have a time-dependent expression on the right, and you have to integrate to find the velocity.
Excuse me, sir.
Yeah.
So when the time is 0, will the velocity be 0?
Where are you getting this? What do you mean?
No, so after we integrate, we'll get an integration constant. So to calculate, how do we calculate the integration constant then?
Oh, the constant. Sure. Yeah, you can ignore the constant. It can be, you won't be needing that. You can assume it to be 0. So we are
the electric field force from the electric field only.
Go on. Sorry, I didn't catch the sentence.
Why the force is taken only from the electric field?
Because we are assuming no external magnetic field, one. And if you are talking about the magnetic field of the electromagnetic field itself, you'll see that the effect of that magnetic field will be a lot less than the electric fields, the force due to this electric field. That is a calculation you can do yourself and see that.
But that will only be true for short time scales.
What do you mean? No, that's not true.
Even over a long duration, it will be negligible.
Yes, yes. It's not long duration or short duration. Both of these happen at the of the time scales of the 1/omega, right? But if you remember this equation for, it's best done okay, it's best done if you think of Lorentz, the Lorentz equation, the force equation in, let's say, the Gaussian units. You'll have E plus V V by C cross B, where in Gaussian units the E and B are of comparable dimension. The dimensions are similar. Only in the very highly relativistic case that V by C term will be significant enough that the force is that the force due to the magnetic field term cannot be ignored. But for non-relativist cases, the V is very small compared to C, that the magnetic field term will have very little effect.
Okay.
Okay, I think, did I mark task 3 or task 3? Okay, a lot of people have done this, I assume. Okay, so this is what we see. It's a simple integration. You have dv and this time dependence only in the exponential. So you have, okay, yeah. So you'll have a minus I omega that goes to the denominator, and this is the current term. You'll see that it is it's a complex term, a factor that is multiplying the E. We have been able to get a current term that is just proportional to the electric field, which becomes very useful for getting the wave equation. The thing to note over here is this equation is very similar to how we define in material the conductive the currents due to an applied electric field. You will have a conductivity term, that is the current will be proportional to the electric field through a conductivity term. And in plasma, for instance, as you can see over here, it is a purely complex number. Now you have this.
Sorry, yeah. Can you go back to the previous slide?
Yes.
Yes, so in the expression here, so when we say J is proportional to E, like in materials, there we assume Ohm's law to be valid, right? So how do we know that?
Yeah, go on.
So how do we know that we can compare the coefficient to a conductivity?
No, you cannot. I'm just saying that the form is very similar. We are not saying this is the conductivity, but just saying that, drawing a parallel that this is similar to the conductivity term that we see in material.
Okay, so we are not saying that this is the conductivity, we are saying that it's analogous to some, like
this is
analogous to sort of a conductivity.
I mean, it is still sort of analogous to conductivity.
Right.
In what sense do you think it will break down?
So, like the way we define conductivity in materials is like if we say that J is proportional to E, and we say that the proportionality constant is the conductivity, right? But
yes,
how do we know that that still holds in plasmas?
Under these conditions of the plasma, you can see that there is a proportionality, complex in nature. As to what kind of solutions it finally gives for the electric fields, that may be different compared to material with just a real conductivity. But you can, I mean, if that's how we define the conductivity as this proportionality between the current and electric field, you can see that even here there's a proportionality, right?
Yeah.
Maybe I'm not understanding the question very clearly.
Maybe I can ask it afterwards.
Sure, we can discuss it. Or at the end, maybe we have other people who work on this field. They probably can give a better answer. Okay, we'll just move on. This would be sort of the only major step then that we'll have to take. And after that, we won't have to spend too much time deriving things. So what we have over here, this Maxwell's equation, we have this current term that we just calculated, and all you need to do is put this back in and try to combine the equations to get the wave equation, right? So I've left out all these gaps in between. Similar to how we did in the vacuum case, just substitute the current expression. I've given that again over here on the right, and the yellow are the things that I've given so that it's easier. Some of the results that we found earlier and some of the identities that you don't have to look up somewhere, but you can take it right from here. You apply the current, find this del cross B equation in terms of E, and then now you can again combine it just like you did previously.
So initially we assumed that there is no magnetic field, right? And
Yes.
from that point, we derive the velocity using electric field. Then why are we, I mean, is this magnetic field from the plasma?
No, we didn't. We assumed that there's no external magnetic field. There is a magnetic field of the waves themselves, the electromagnetic waves that are propagating. They have an electric field and a magnetic field, right?
So shouldn't that be included in the expression for Lorentz force law?
Yeah, that is what I was explaining earlier, that the effect of the magnetic field on the charges will be negligible because the velocities are very small compared to the speed of light. If you think of the Gaussian electromagnetic force law, then you can see that it is E plus V by C cross B, right? And that particular expression has a significant term for the B field only when the velocities are high. Otherwise, only the electric field is important.
Sir, I have this question that they will produce some curvature in the trajectory of the electron.
Yes, that's what we are discussing about, that curvature will be negligible. But you can, even in SI units, you can actually calculate these terms later for this assumed. So in electromagnetic field, okay, even in this case, you can see that the electric field and the magnetic field have a proportionality, right? In the transversely moving electromagnetic wave. I think yes. The B would be K cross
E by C, 1 by
K
C.
cross E by C, right?
It is yes, 1 by C times E.
Yes. So you can see that we have the electric field. You can substitute the B value, that is K cross E by C, and you have to take a cross product with the velocity, right? The velocities are very small and it's divided by C over here. So the second term is much smaller compared to the first term, which is simply E.
Okay, sir.
Is that clear now?
Yes, but over a cycle, is that curvature in the trajectory nullified?
I mean, it may not be nullified, but it's a very small term. You can see that it is, for non-relativistic thing, it's close to zero. The effect, the force that it's experienced due to the magnetic field is essentially zero. So it won't even curve much.
Okay.
I hope this is clear to all. Then for task 4. Task 4 is just substituting. You have the value of J, which You put it in the equation 1, and you have this time dependence of E that we know. You take the derivative of it so that you can take E common outside, and the value in the parenthesis will have no time dependence. Then you have these two equations. You can combine this del cross B with the del cross E equation of the Maxwell's equation, and you can get something very close to the wave equation in the case of a plasma. Yeah, the first bit might just have a little bit of algebra, taking the common terms and all that. But as long as you have the expressions, the variables right, it should be all right.
Sir, what is the typical order of N, capital N?
Oh, yeah. For the ISM, it would be about, I think I saw value 0.0. You can consider 10 power minus 2 per centimeter cube or something like that. But it depends on the region. You can apply it for a much larger range. For instance, the ionosphere, I think the density is about 10 power 6 or something like that. So it can range from I guess something like 10 power minus 3 to 10 power 6
per centimeter cube.
Yes, yeah, in CGS units for astronomical purposes.
Okay.
Okay, I can see a few dones and we might be running out of time. So I'll slowly go over what comes about. So it's just, if you see the second step is just the substitution of J, the current that we derived. And then we are just taking some terms common outside. The significance of it will be apparent shortly. And then we just combine it because right now we have two equations, one del cross B, proportional to E, and you have this del cross E term, and you get something similar to the wave equation, del cross E, and it's just proportional to E. Now we are considering this to get this specifically the dispersion relations. We are considering one of the Fourier components, and as you can see in the identity over here, this it will require some taking the cross products essentially, but one can show that if you consider a wave moving in the k direction, and you take the cross products, or you take the curl of the curl of one of these Fourier components, which has this exponential ikx dependence on the spatial coordinate, then it can be equivalently written as the wave vector times k dot e minus k square e. Just like how in curl we had a gradient of a divergence and the Laplacian. Okay, so this part is clear. That we have almost reached the end. We'll be able to make inferences based on this. I hope you guys could stay together. If I had, not made you do all that algebra, if you see a slide like this, you might get totally confused. But right now, you understand where it comes from. The expression on the right over here in this sort of wave equation is essentially the combination of the current and the dou E by dou T term. Now we'll try to interpret what is exactly. Now we have a description of the electric fields in the plasma, and we'll try to see what it implies. So this is the expression that we got with all that jugglery in the back just before. Now what you can focus on are two different modes of the electric field. This is not in vacuum anymore, so there can exist longitudinal modes of the electric field. And of course, the thing of our interest, the transverse modes, where the electric field is perpendicular to the propagation direction. But first we'll look at just the longitudinal mode where the propagation direction is parallel to the electric field, which means k dot E, the expression that will come in this first term over here, will just be k times the amplitude of the electric field. So you can apply that over here, and you'll see that the left-hand side of this equation will just go to 0. And what you're left with is this expression on the right, with this factor omega square minus ne square by m epsilon naught multiplying the electric field. And the electric field now, by definition, is just the longitudinal component. Now, for a non-zero longitudinal electric field, this would imply that omega square will have to be equal to ne square by m epsilon naught. Now, this quantity ne square by m epsilon naught, quite a mouthful, is actually, you can see that it has the units of frequency. And so far, I did not reveal that it is what is the plasma frequency. Now, one does not have to go through this derivation to get the plasma frequency. Plasma frequency is just the natural frequency of vibration of a particular given plasma, a cold plasma with a particular density. You can see there's a density term over here. So independently, one can derive this frequency just by giving a perturbation, so that the electrons are essentially displaced from their equilibrium position. And if you consider for small perturbation a restoring force proportional to the electric field, then you can see that naturally the electrons in the plasma will oscillate at a particular frequency, and that will come out to be this expression square root of NE square by M epsilon naught. And through a seemingly different derivation, where you are essentially perturbating the plasma using the external electric field of a radiation, we are able to get one of the components is that oscillation, which causes longitudinal electric waves. Now, what we are interested in is the transverse mode, which is where the transfer of energy happens in our electromagnetic radiation. And for that, you explicitly choose the direction of propagation perpendicular to the electric field, which means k dot E equals 0, which is this first term over here. It goes to 0. Then you are left with a simpler relation between the k and the omega. You can see that it's minus k squared. Now, these are the transverse electric fields of the electromagnetic radiation. And it has this dependence on the omega. And you could change this to omega p squared, as we'll shortly see. So that is what we have done here. So this is the dispersion relation in the cold plasma for the conditions that we had outlined before, when electromagnetic waves are incident on it. You can find the k, you can find the omega. Now let's try to see what it implies for the modes that are allowed in the plasma. So the transverse modes, the allowed modes will follow this relation. It's in plasma physics, it's customary to draw these omega k spaced plots and try to see which modes, which particular combinations omega and k are allowed, which ones can, you can show both the longitudinal modes, transverse modes, and try to see which ones lie where and what relation is followed. So this is one of such plots. You can see this is the k for the magnitude of k, and this is the omega, the frequency. And in vacuum, you can see these are the relation between omega and k that represents propagation in vacuum, which is omega equals ck, as we saw first. Now, if we try to plot the relation that we found for this cold plasma, these would be the curves. Minus k just representing motion in the opposite direction to x-axis, let's say.
Sir, it looks like some kind of light cone. Just the difference is that the coordinates are different. Here it is omega.
Exactly. It is, it is, you can draw parallels to it, and you'll soon see that you can define velocities depending on how the inclinations are different corresponding compared to this omega equals ck line.
Then the omega and k part is just analogous to that time and space part.
These are the conjugate variables, right? As you saw by definition.
Okay, sir.
Mm-hmm. But you'll see that the superluminal and subluminal are, I think, flipped because of that reason. Okay. So this is how the plot looks. We can try to see slightly deeper of how to interpret this particular curve. The first thing you can immediately note, even without going any further, is that frequencies from 0 up to a particular omega p, which is that term we defined, root of NE square by epsilon naught m me. All these frequencies do not have any solutions. They do not propagate. Okay, exactly at omega equals omega p, there is a longitudinal mode, but rest of the frequencies, if radiation of frequency less than the plasma frequency falls into, tries to pass through this plasma. It's mostly reflected or dissipated, but it does not get through. That is something you would have heard it multiple times now, till now, in many of the lectures, that a particular medium has this plasma frequency, and that is why we do not see frequencies up to a particular range. The value that I defined about 0.01 electrons per centimeter cube, if you try to calculate the plasma frequency, it falls in the kilohertz range, near about 10 kilohertz or so, a few kilohertz. But as you go through denser and denser medium, it could easily go to the megahertz range. And that is why I think for the ionosphere, if you calculate it out, now that you know the expression, you can easily calculate it out. I think it comes to about 10 megahertz or so. So frequencies below 10 megahertz will not get through the ionosphere to us on the ground.
So below omega P frequency, they will be reflected or absorbed, or
mostly reflected, some absorbed as well.
Okay.
Mm-hmm. I think one can show it because, okay, you can see over here, there's this dispersion relation. You can see that if omega is actually less than omega P, eventually the K will be an imaginary part. It will have a, I mean, it will become imaginary. And then when you try to see how the solutions look, it will have a dissipative term, and the rest of it will be reflected. Now, what you're interested in is in the propagation of the velocity at different frequencies. And for this, one has to look at the group velocity. Now, to understand group velocity, you can make kinematical arguments as to, you're not just considering one frequency that is propagating, you're considering perhaps a narrow frequency range in which all frequencies are propagating. What you'll see is that you'll have a sort of a wave packet, an envelope that contains all these frequencies that always moves at a different velocity. It is different to the phase velocity that you can calculate for a particular Fourier component. Now, it turns out that kinematically, you can show that the group velocity of such a electromagnetic wave that is composed of all these frequencies in a narrow range can be derived by taking a derivative of the frequencies with respect to the wave numbers. I mean, you can look up derivations for this. This is just a kinematic argument. A more fundamental understanding requires understanding how the energy gets transported if you're considering waves spread over a particular range of frequencies. Now, as it turns out, it is not as straightforward to understand why a kinematic relation such as this is directly related to the dynamical concept of how energy gets propagated in these waves. But I mean, I still have to go through it, but such an explanation is given in one of the appendices of this particular book. You can look it up, by Andrew Sturrock on plasma physics. But I'd like to qualify that it's not straightforward. But we'll take it as one of the results for now. We'll say that we'll use this kinematic expression d omega by dk, and this does in fact explain how the energy of a particular wave packet propagates. So the velocity will be given by d omega by dk, which you can apply it because you have this dispersion relations for the plasma. And you can see the plasma frequency has been, the variable for the plasma frequency has been substituted. So it looks a lot more cleaner over here. And for frequencies that are much greater than the plasma frequency, which for instance, our case of ISN, we saw that it was about a few kilohertz. If you're observing in the megahertz range, you can simplify it to this, by doing a series expansion and keeping only the leading term. Now, using the plot, we can also try to understand how these velocities at different frequencies behave. So you can see at exactly the plasma frequency, the curve is at its minimum, which means a tangent over here would be near horizontal, and this would correspond to zero velocity. But as you move ahead for different frequencies, as it goes slightly up in frequencies, you can see that the velocity is non-zero anymore. And as you go away more and more higher and higher frequencies compared to the plasma frequencies, the velocities keep increasing, the group velocity. And eventually at very high frequencies, it's nearly parallel to the vacuum omega equals CK line, which means that at that stage, at very high frequencies, it goes close to the speed of light. That is why, especially if you consider the extreme cases of X-rays, gamma rays, nobody worries about this dispersion delays. Even for timing pulsars, in X-rays and gamma rays, we don't worry about it because the effect is negligible. To convert this velocity that we have figured out into these dispersion delays, you'll have to first calculate the time taken to travel distance d. That would you'll have to imagine a wave that is propagating from a particular astronomical source to Earth, and you can and in between the densities could all be very different over at different distances. So you have this integral to find the total time traveled. You'll have this distance element dl, and you'll divide it by the velocity, group velocity, and you'll have to integrate it over the distance from the source to the observer. One can use this formula over here. It's an inverse. So again, that series expansion is used to convert this minus to plus, and you'll have this expression. Now, remember, you can clearly see that you just have to retain inside the integral only the terms that are dependent on, that has some dependence on where it is, or the distance, or the spatial coordinate. You'll see that omega p, which is a plasma frequency, is the only one which has this particular term, that is the electron density, number density. And that is something we expect it could be different at different distances. So everything else, these are constants. And the one just gives the d by c term, which is the time taken if there were no intervening media. So dispersion delays, you can calculate by taking the difference of t and d by c. The constants all come out, and you have this integral ndl. Now this integral, okay, we'll come to the astronomical context, but in plasma physics, this is the end of it. You can calculate the delays just by using the SI units. You'll get, you can see it's in microseconds if the value is calculated per meter cube, and you have this frequency dependence over here. Now, in an astronomical context, what we do is this term, which is, we cannot always easily model, but we can use this as a variable that you can find by observations, as it has been discussed briefly in many of the lectures. Since you know the delays that we can expect at different frequencies, so this dispersion delay given for a single frequency is compared to infinite frequency, of course. You can convert this so that the densities are now in per meter per centimeter cube, and the distance is in parsecs, and the frequencies are in megahertz. Then now this is again just a change of units that you can do, and you'll find this is the expression, and this is what is commonly shown in astronomy, and this is what is calculated. If you make observations, you can at different frequencies, and you can find the delay, you can get the dm value, which is the integral of the electron density along the line of sight. This is what we had showed yesterday in the experimental part of the, if you remember, the dynamic spectrum. So this plot shows the intensity as a function of both time and frequency. So, and these streaks are for the signals of the Vela pulsar. And you can see that higher frequencies come earlier and the later frequencies come later. This is just the direct proof of whatever we derived over here, the dispersion relation. So it's obvious that the radiation has come through intervening media, which has dispersed the radiation. This, as I mentioned even yesterday, this is assuming, understandably assuming that the emission is emitted simultaneously as the source, which we have good reasons to believe they are. Now, okay, yeah, towards the end. So I'll leave with these final words. In a sense, we have just taken a small step in the direction of trying to understand plasma physics. And we've used the dispersion of radio signals of particular importance to radio observations to do so. So I think you have a much better feel for how exactly these dispersion relations under these simple conditions in the linear regime comes about. And I hope you'll be able to appreciate the fact that even with such restrictions that we applied, it matches, you'll see, okay, when we do the actual hands-on experiment part of it, you'll see that it matches very well with what we observe. So although those conditions sounded a lot restrictive to begin with, it works quite well for the resolution of the measurements that we can make. It suits perfectly. Now, the original idea when I signed up for this talk was to go beyond this and talk about Faraday rotation, which is a level higher than what we have encountered over here, because the magnetic field, so Faraday rotation is apparent when there is an external magnetic field. You can assume it to be, a uniform magnetic field in that the plasma is in, and the electromagnetic radiation goes through it, how it changes the polarization of the electric field. Now, this is a very good step to take after, if you have completely understood the dispersion relations that we derived right now for the cold plasma without the magnetic field. And I would strongly urge you to do that. You should appreciate that these are just the foundational steps that we are taking. It may seem very small to just focus on something like just the propagation effect of electromagnetic wave in plasma, but it has serious implications and can be extended to a wide range of phenomena. Because the plasma, as you saw, is extensive. It's all over in the universe, the stars, the sun, galaxy, compact objects, AGNs, and galaxy clusters. All of them have plasma of various conditions, various compositions, and so on. But the techniques are essentially the same. If you have to learn the plasma physics, you're observing radiation that is coming from these systems. And these are affected directly by the plasma conditions that exist over there. So this is a field, I mean, you have focused on a very small initial, we have taken a very small initial step, try to understand a simple concept. But if you go further in it, the applications are nearly endless as to how you can you can figure out a lot about all these systems by trying to understand the plasma conditions over there and using the electromagnetic radiation that we observe from it, how they are affected by these plasma. Okay, so that is it. At the end, I would really like to thank Deepanjan, who is with us still, I think, yeah, through this talk. He's a professor at NCR8, and he has been very helpful in discussing a lot about plasma physics. A lot of my intuitive understanding comes from discussing the results with him. It has been very helpful, and we are planning to work together in trying to, create possibly lectures and material in the future, not just about Faraday radiation, but other things of interest in plasma. And any big picture questions about plasma and all this, I may not be able to answer it. Deepanjan here will be able to answer that. So you can ask any questions regarding those two. All right, thank you.
I have a question.
Mm-hmm.
So the situation with plasma and the variation of propagation speeds with frequency seems very similar to how a prism, in a prism, the speeds of light propagation are different.
Right.
but in prism we also see dispersion, like dispersion in the sense, in the angular sense, that different frequencies get split in the angular domain. So
the velocities, or because of the refractive index, the velocity is also different. That is why.
Yes. So do we not see like different frequencies getting split in different directions in the plasma situation? Or do they still propagate in the same direction?
It should get deflected. If you apply, I mean, so you can, define a refractive index for this. It will be square root of the relative permittivity that one can calculate from these equations. And if you actually apply, I mean, I would assume you can apply the same mechanics of, incident radiation. But the only thing I'm worried is maybe it's not as well defined.
No,
you cannot define a very well defined interface between vacuum and plasma.
No, I think the angular deviations are caused by the interfaces and the angles. Okay, the refractive index changes will do the needful if you make a plasma prism.
If you can have like an interface where it's
of plasma are not going to do the angular dispersion.
Say that again.
The angular dispersion is not going to be caused by parallel slabs of plasma.
Right.
The manifestation in the angular dispersion is because of the inclination of the interfaces and the fact that the refractive index is different at different frequency. That fact remains. That's a common fact. Okay, that for plasma also the refractive index is different at different frequencies. So if you make a plasma prism, you will see angular dispersion, but not otherwise. Angular dispersion is a manifestation of not just the refractive index being different at different frequencies, but because of the geometry of the interfaces.
Right.
So whenever in this astrophysical situations, when
you can make a plasma lens also. Okay. You can make everything that you can make with the normal material. Okay. On the Earth, and you will find that the plasma lens will actually be divergent. A convex plasma lens will be a divergent lens, as against the glass lens that you would make, which will be convergent if it's a convex one.
Okay, so in all the astrophysical situations, the radiation is always like facing parallel slabs of the plasma.
When the plasma is there, you can model it as anything because you would like to see that as the relevant quantity, right?
Yeah.
These are transverse waves, right?
Yeah, okay, thanks.
Like in case of pulsars or that fast radio bursts, like do you see that plasma lensing effect also as those waves travel through the plasma?
Well, there is no comparison. Okay, there could be lensing happening at that instant. We do not have a situation where the lensing was not happening, right?
Yes.
There are situations for persistent sources that you can see the effect of a plasma lens coming in the line of sight and going away. Okay, and that leads to something called extreme scattering events. If you were to search for a keyword, have a look at extreme scattering events in radio. You will find equivalents of this.
Okay, sir. Thanks.
Actually, just to add to what Desh has said about the prism, I mean, once the ray is refracted within the prism, it actually continues, right? It's only the interface that the refraction actually happens.
Correct.
Yeah. Dipanjan, since you're here, you would like to add something? Hello,
no, it's a very good talk.
Thanks. Any other questions?
If some students have something later on, they are most welcome.
Yeah, I had a question regarding the derivation.
You can also say observationally, one very interesting thing is seen, which is that there is a lot of dispersion measure changes that one sees when you observe a pulsar or something. And the change in the dispersion measure is basically the change in the electron density. So there's a change in the plasma frequency. And this is an observable effect. Now, if this plasma changes by extreme amounts, then additional things will happen, like this, that there is extreme scattering event and so on. But scattering is not due to the uniform density, but due to the fluctuation of the density. Okay, so it is another effect that one is talking about.
Right.
But at this stage, observationally, what we are comfortably observing regularly these days is that the dispersion measure is seen quite a stable quantity, and there are very fine changes in dispersion measure, which is an indication of small changes in the interstellar medium. Partly because the pulsar also moves with very high speed, so it samples a slightly different medium. Desh, you agree with this?
Yeah, I would just like to add that you can have actually a scattering always brings in a sort of certain randomness and the statistical description of it. Here you can have a pure refraction alone describing the propagation of the waves through a well-defined, well-shaped plasma lens, okay, in principle. And it will do exactly the way we understand in optics, except you have to take into account what the refractive index is, and then you will be it will be apparent that a convex lens will be a diverging lens, and vice versa. But you don't have to invoke scattering and the spread of ray directions. You can actually do even ray optics here, simple ray optics, and see the refraction effects to drive home the point that a lens like this can actually do very systematic stuff.
This is effectively refractive scintillation you're talking about?
Well, it could be just simple refraction also.
Okay.
Simple direction change. Of the,
Okay. Yeah, sure.
These are interferences after, of course, you invoke these.
After refraction.
And the manifestations of combinations of these.
Sure.
Absolutely. Yeah. Yes, but what the regime of description here is absolutely right. The term used will be the refractive effects. So the refractive effects, are on top of the diffractive effects that we, where we will take this overall description.
Sir, I have one question.
Yeah, Vishwas is a question.
Sir, here we have assumed the collision-less plasma, right? The dispersion relation. So, can we also model ionosphere as a collision-less plasma, or is it not true in general?
I'm not entirely sure what exactly it is. The results still apply. Observationally, we can see that this result still applies. But are collisions important? Desh or Dipanjan, do you know, in ionosphere?
Yeah, let me just first define what you mean by a collisionless plasma. It is that once you take the wavelength of your particular frequency, the wavelength should be smaller than the distance between the two particles. Okay, so when you have such a situation, you would say that the A is equal. So, for example, if you have number density n, then n to the power minus 1 by 3 is your roughly the distance between the particles. And so your wavelength has to be smaller than that. So for these wavelengths, it will remain collisionless. And for the wavelengths which are larger, they will not be, they will be collisional because they can now interact with the particles as they propagate the waves. Now the second issue is that yes, for radio frequencies, the ionosphere does act as a collisionless plasma, and we see the effects of dispersion measure, just as Prakash is saying.
Okay. Thank you, sir.
So I had a question about the derivation we did today. So we solved for the electric field using Maxwell's equations, right? Yeah. So in Maxwell's equations, we took the constants as epsilon naught and mu naught. But the fields are propagating in a medium, right, which is the plasma. So why did we not consider epsilon and mu instead of epsilon naught and mu naught? Why did we consider the vacuum quantity?
Actually, if you'll see, epsilon is what we in fact derived it. So the velocities, if you look at the dispersion relation, the epsilon can be obtained from the derivation itself. So the relative permittivity, what we used over there was just the vacuum permittivities, but plasma does have a relative permittivity. That is what comes across as this velocities that we calculate as well. So I didn't explicitly show it where how the relative permittivity looks, but that is what we calculated. So this the simplest way to think of it might be to take the del cross B term and equate it to let's say an epsilon E, the 1 over C square dou by epsilon E by dou T, and you can try to use that over the derivation here and try to see what is the epsilon relative permittivity that comes out. So implicitly there is relative permittivity here.
And so, but the doubt I had was, while deriving the electric fields themselves, why did we consider propagation in vacuum? Because the fields are propagating through a medium, right, which is the plasma. So I'm assuming the plasma is like the plasma completely fills the gap between the source.
So I think the confusion is coming in how we use the electric field initially in vacuum case for calculating the Lorentz force, right? So the way to think about it is that using that electric field to calculate the force initially just as a perturbation. Now, but when we use the full Maxwell's equation in plasma, we are not just focusing on the electric field of that initial electromagnetic wave that caused the perturbation, but we are solving for the resultant electric field in the plasma itself. So it doesn't come across as obvious, but sort of way to think about it might be that the initial field, we use it to perturb it a little bit, and it's not a time dependent problem we are solving. We are then saying that that is something that is going to keep on happening in a sort of steady state way inside the plasma, that particular driving force due to the electric field of the incident radiation. But now what we have in the steady state of the plasma, because of that effect, is there is a resultant electric field, which is defined, which is a combination of everything. That is it is the resultant electric field. It has contribution due to the electric fields in the plasma and the radiation. And that is what we solved for. And that is why we had this propagating longitudinal waves as well as transverse waves at the end. Is that clear?
So could you go to the Maxwell's equations in the plasma, which you task 4, I think. So here I don't understand why we are taking mu naught J instead of mu J, because these are equations in the plasma.
Right. And no, you can take a mu J. But permeability itself, if you see for plasma, the relative permeability is nearly 1. So it is sort of implicitly assumed.
Yeah, that's what my confusion was. Okay. But suppose we had some medium or some plasma which had like a significant relative permittivity. Then in our final formula, which we got for the dispersion medium, there we would have to integrate over the epsilon which we get in the denominator, right?
Yes.
We cannot take that out.
The permeability is the relative permeability is close to 1 here, not the permittivity. Permittivity is something we can get it from the solution, depending on how we express it.
So you had mentioned that we are taken mu to be near 1 or near mu naught for the plasma.
You're talking about mu, right?
Yeah, mu.
Yeah, mu is permeability. The relative permeability is 1.
Yeah. Because the relative permeability is very close to 1 for plasmas.
Yes.
So we could substitute mu naught in Maxwell's equations instead of mu.
Yes.
But I was wondering if there are any media or any astrophysically relevant media where relative permeability is not close to 1. And in that case, the Maxwell's equations would have mu, right? So while calculating the dispersion medium for such plasmas, if there are any, we would have to integrate the mu also while calculating the dispersion medium, right? We cannot take that out of the integral there.
Yes, that's correct. So it would depend on the situation, but I mean, honestly, I don't know enough about what would be the condition under which mu, the relative permeability will be different than 1. I know that in these cases, the cold ionized medium, it is tenuous medium, definitely it is close to 1.
Okay.
What about plasmas near the poles of the planets where the strong magnetic field will be there?
I suppose so. I'm not entirely certain. I haven't explored too much about this particular aspect of plasmas, unfortunately. Do you have any experience, Professor Krishna?
No. I'm just guessing that
it might be relevant.
Under strong magnetized plasmas, as they call it,
right.
There should be, I mean, apart from the anisotropy,
right,
introduced by this magnetic field, in the other direction, perpendicular direction, I do not know whether the mu will still be mu naught. I'm just curious.
I know that in cold plasma, when you derive this Faraday rotation, the relative permeability is still close to 1. Strong magnetic field, I'm not certain. It is likely that the mu may not be close to 1, but.
And the other thing I wanted to ask was about in the absence of an external electromagnetic wave, the plasma would have electric and magnetic fields spatially distributed, temporally and spatially varying.
Yes, we considered sort of this this particular model that for which we derived, it was stationary. It is a sort of unphysical process, but it's not, there's no strong variations that are going on. You can introduce a perturbation where you try to take the electron charges away from the equilibrium position, and then they would oscillate and produce these plasma oscillations. But other than that, there are no significant uncompensated electric or magnetic fields, because there are free electrons that are there. They'll try to compensate them.